It is said that almost 100 years ago, M.C. Potter, a botany professor at the University of Durham in England, was among the first to discover a process by which energy could be extracted from E. coli bacteria. Today, microbial energy sources are a promising concept. When integrated with organic materials, such as compost or waste, bacteria metabolize the nutrient-rich medium, releasing energy. An electric charge is generated when a conductor, such as an electrode, is factored into the system. The promising concept of microbial energy may one day prove to be the alternative source for the energy we need. Currently, research on more efficient bacteria is needed in order to generate an electrical current that would be capable of sustaining the greater energy demands of today's technology. The geobacter bacteria grow in the soil medium by oxidizing organic compounds to form carbon dioxide. For this redox reaction, the sole electron acceptors are the microbial cell electrodes. The electrons generated are recovered as electricity approximately 95% of the time, flowing in a galvanic cell circuit path from the anode to the cathode. Protons are also transmitted up through the sediment and the water to the cathode. The electrons flowing through the wire to the cathode recombine with the protons as well as oxygen from the atmosphere, and together form water as the overall product of the reaction. Given this green process, microbial energy technology should be further researched. As such, it is our intent to inform and educate students of all ages, with the hope that this alternative source will attract future scientists into further exploring the potential of the microbial concept. The round graphite hanging just beneath the water surface is the cathode. The anode, a much larger piece of graphite, is buried in the soil and anaerobic for the most part. The batteries generate approximately 300 millivolts of charge each. They are attached in a series and can generate a total of 2.6 volts. A 1.7 volt LED light bulb is illuminated by the bacteria battery alone. Although the system generates up to 2.6 volts, the amperage is insufficient. A 100 ohm resistor was attached in the circuit. The consistent amperage flow was approximately 383 microamperes. A 1.2 volt capacitor with an amperage requirement of 120 milliamperes was removed from the toy car for demonstrative purposes and charged separately in order to build up enough charge to run the car experimentally. The batteries were connected to the capacitor for several days in order to build up the charge to 1.3 volts. The car you are seeing is running off of the electricity generated by the bacteria.